SwayamPrabha. Digital India. Educated India.
This lecture is on engineering applications of vibrations. So far we have studied about the basics of engineering vibration. Today we will see in this class what are the basic engineering applications of vibration, and towards sometimes in the middle of the class we will see how vibration is used for the health monitoring of machines or condition based maintenance of machines. Okay. Some of the topics which we will be discussing today are essentially what happens during the case of a base excitation. For example, if you have a surface, okay, and because of certain forces there is a motion on the surface, and how by putting a sensor we can measure this motion y and sense it as a response x of the sensing element. This is the case of base motion. Usually and typically when we have a vibrating surface, we try to know what y is. How do you do that? We put an sensing element x, or which will be essentially housed in a transducer. So is proportional to y, or what is the relationship between x, y as a function of the frequency, etc. Okay. So once I can measure x, I know how it is related to y, okay, and that is what we are going to study in base excitation. Another very important applications of or unwanted vibration is this rotational unbalance. Essentially what we have is any shaft which is supported on bearings, suppose it carries a set of blades like in an impeller, and this undergoes rotation. Imagine in this impeller if there is an unbalanced mass m or me. This unbalance was at a radius of r from the axis of rotation of the shaft. You can imagine the unbalance, radial unbalance force F unbalance will be me omega square r, where omega is the speed of rotation. Now you see this unbalanced force, because of the centrifugal action of the unbalanced mass, is proportional to omega square. Omega is the rotational speed. It is almost very small if me is small, r is small, and omega is small. But even if me and r are small, but omega is large, like in the case of gas turbines, rotating at 30,000 rpm, a small amount of unbalanced mass is going to give rise to unbalanced force. And what will happen essentially is, because of this unbalanced force, there will be forces coming up to these bearings. Okay, that depends. This F1 and F2 depend on the position of the impeller and so on. And further, this will be complicated if there are sets of impellers. Like in a gas turbine, as you will see, there will be different stages of compressors. So one set of compressor having a lot of vanes in that impeller, and if one such vane has an unbalance, it is going to lead to unbalanced force, and this unbalanced force in different planes is going to give rise to couples, and then this is going to have a complicated effect in the life of the machine. It is going to affect the bearings. Bearings will be subjected to fatigue failure. There will be clearances will increase, and it is going to complicate the matter. Okay. So we should try to avoid this problem. Okay. Now another situation we have in the engineering application is vibration isolation. wherein suppose I have a machine, okay, which is put on a foundation. Because of the dynamics of the machine, certain forces are being subjected to the ground, and this ground is going to then vibrate, and this waves will get transmitted, and then at some other place I have another machine, and they are going to affect this machine's operation. So, I have to devise a mean wherein I reduce this energy which is getting transmitted from one machine to another. This is one way of looking at it. The vice versa also happens. For example, you are driving on a road on a vehicle, and there are lot of roughness, potholes, etc. So, these are going to give rise to forces, okay, and these forces are going to get transmitted, and then you are going to get a sense of vibration to the human being who is sitting in the car. And obviously, we would like to isolate this frequency which is coming from the ground, this motion which is coming from the ground, by a proper selection of what is known as the vibration isolators. We will discuss about them in the subsequent sections. So, the vibration isolation is another serious problem in engineering vibration, and then we will see how we can avoid it, how we can reduce it, and so on. Another application of vibration is this tuned dynamic absorber. What happens? Suppose I have a body, which has a mass m and stiffness k. So, omega is equal to root over k by m. Okay. This is the primary, this is its natural frequency, and this is the primary mass. Now, to this system, if I see the response of this system, I will get a natural frequency, a response at its natural frequency, which is omega is equal to root over k by m. And say for example, this amplitude x which I have got here is something which I do not like. I would like to reduce this vibration amplitude. So, what I could do is I could attach to this system another system wherein this omega is also equal to its ks and ms. So, this system now is going to have a response which will look something like this, because there are two bodies, there will be two natural frequencies, and there will be a natural frequency shift, and most important thing is this amplitude of vibration has reduced. So, the primary mass, though the natural frequencies have shifted, then but the amplitudes of vibration has reduced, and particularly this has applications in for example, large skyscrapers, for example, because of the wind blowing. You can talk about the tall hotels in Dubai, okay, or the skyscrapers of New York or San Francisco, etc. When this wind is blowing, these skyscrapers have a motion, and this at the top could be about 1 meter. Imagine a 100-story building, on the top it is swaying about 1 meter, and this kind of motions could be arrested. Suppose we put such structural tuned dynamic absorbers in the structure itself, so that they are going to arrest these motions and reduce the amplitude of oscillations. This is one application of tuned dynamic absorber. There are a lot of applications of such tuned dynamic absorbers in automobiles. For example, if you know the drive shaft or the propeller shafts also undergo a lot of torsional oscillations. So, we can put such torsional tuned damping absorbers to reduce those oscillations at the natural frequencies, because by tuned dynamic absorbers we can reduce the oscillations of the primary mass because of the resonant frequency of the secondary mass. Another engineering application is this torsional dampers. You recall, I had written this equation I t theta dot plus C t theta dot double dot plus k t theta is equal to some function, forcing function torque. So, by introducing this damping term in oscillating systems, by having a torsional damper, I could reduce the oscillations or the rotational response of the system. For example, a crankshaft of an engine which is having rotary motion, and its torsional oscillations could be reduced by putting a torsional damper. So, these are some of the applications, and we will see some practical examples now. To begin with, if I look into this case here, in the case of a tractor platform isolation, here we have a tractor. For example, of course, this is the platform where you put the foot. In case this is me in my younger days, used to test on a tractor, and this is a platform here, and if the driver sits here, because of the engine's dynamics, okay, none of the vibrations from the engine should get transmitted to the platform, to the seat, etc. So, how do they arrest that? If you will look closer here, there are actually what are known as the anti-vibration rubber mounts in this location here between the platform and the chassis of the tractor. So, the chassis of the tractor is actually supporting the engine. So, the forces from the engine, because of the engine's excitation, the engine's excitation forces and the inertia forces, the engine excites the structure. So, this chassis is going to have large motion, and if this platform was rigidly connected to the chassis, all this energy is going to get transmitted to the platform. Instead, we put a flexible element. You can think of it as a structural fuse, or you can think of it as an structural impedance mismatch. The energy which is, if you analogous to an electrical circuit, if I have an impedance mismatch in the system, the current is not going to flow, or the power flow will not be maximum, and same is happening here also. The mechanical power flow is reduced by having an structural impedance mismatch, which is created by this vibration isolator. So, depending on the payload being subjected to the isolator, depending on its mass, the frequency of operations, I can decide on the natural frequency of the oscillator, I can decide on the stiffness characteristics of this isolator. This is another such view of these isolators, and these isolators just need not be elastomer or polymeric mounts. They could be also spring mounts, because this elastic mounts, they wear out with time. The elastomers, sometimes they react with the oil and they lose their properties. Sometimes they react with the saline atmosphere, etc., around you, and then they will lose their structural stiffness and their bonding strength. So, sometimes in many harsh applications, people use other kind of mounts, which I will come to later on. Now, this is the case of a gas turbine, wherein this turbine rotates at about 30,000 rpm, and then there are series of such impellers which will be the compressor and then the turbine, and this compressors, there could be many such blades in the or vanes in the impellers, and if one such set of compressor ring undergoes an unbalance, it is going to give rise to a radial force. Suppose another one has another amount of unbalance, it is going to give you a radial force. So, there could be a couple. So, in this couple, they are going to give rise to a lot of forces, though this turbine is put on a structure here or a platform, and this platform is rigidly mounted to the hull of the ship or fixed to the wing of the aircraft. So, now this is a closer view of this compressor. Imagine all of these rotate at 30,000 rpm or 20,000 rpm. Imagine if one such vane either has a small amount of unbalanced mass, you can imagine the kind of forces which are coming onto the bearings which are supporting them. So, unbalance at high speeds is very, very dangerous, and in fact this amount of unbalance depends on the severity of the machine. Suppose it is a very high speed machine, we will have serious consequences. So, for example, you are talking about a high speed machining operation where we have a spindle and there is a amount of unbalanced mass in the spindle. Suppose you are doing a vertical boring, and if there is an unbalanced mass and because of this there are radial forces, you will never get a true bore. Okay, there will be ovality in the bore. So, all these are going to affect the performance or the your output of the machine. It could be a machine surface, it could be a gas turbine, it could be an effect on the, it could affect the bearings. So, these are actually the causes by which the machines fail, or the reasons behind which machines fail. If one such unbalance goes unnoticed and we only get woken up when the bearings fail, but the problem could have been an unbalance usually has created this. So, it is very, I mean, people do that once they install a machine, they ensure that the machine is balanced perfectly to its operating speed, and in the subsequent classes I will also be telling you how to do a field balancing of such a large gas turbine or a fan which is rotating at high speeds. Basically, what happens, I should briefly tell you here in the radial plane. For example, if this has a lot of, you can call it vanes, blades, whatever. If there is a small amount of unbalanced mass and this is rotating, and in this machinery, and this of course in there in a casing, etc. Okay, and I measure this response here. By some technique, if I can find out this amount of unbalance, and if I know the location of this unbalance physically with respect to a certain marker in this vane, I could put a correction mass, okay, in a single plane, and then I will have a balanced rotor or a balanced disc. But if there are multiple such discs along the length of the shaft, I have to make sure that each one of them is balanced. Otherwise, if I have a balanced here, okay, if I have a balanced mass, unbalanced mass here and a balanced mass here, I may be balancing it in one plane, but the couples will still be there. So, this is also something which we have to be careful about. Another application, or I should show you, is this anti-vibration mounts. For example, this is a setup from our lab. When we have the system running, there will be a lot of forces coming onto this structure, and this structure will eventually transmit to the foundation. So, these are what are known as anti-vibration mount. You can see one mount here, another mount here. So, imagine if next to this machine I had a very sophisticated laser based measuring systems, okay, an optical table wherein this is a table, okay, and there is a laser beam being produced, and then it has certain target which it has to hit or strike. If there is a small amount of oscillations because of certain ground vibration, so what is going to happen, that this source is also going to have a motion. So, I can never hit my target by laser beam, and there are many engineering applications wherein lasers are used. Lasers are used in microscopy, lasers are used in machining, lasers are used in surgery. Imagine if such laser beam, imagine a doctor coming to your eyes to do a laser surgery and his hands are shaking. Okay, and now I bring it back here in an optical measurement table, because I have a large, imagine you have a large forging hammer in your workshop next door. Okay, of course, you have made a nice building and then there are nice walls, etc. So, the workshop, and then you have a lab here, you are doing a laser lab. Okay, because of the forging hammer, a lot of forces are coming, and then these forces come to the ground, and then this are going to get transmitted through the ground, and then they are going to affect the laser. and this is not a science fiction, it does happen. There has been instances where I have measured vibrations of the level of micro g. Micro g is 10 to the power minus 6 g. Okay. In fact, wherever when we have laser based measurements, the vibrations have to be less than 10 to the power minus 6 g okay, meters per second square or whatever, with that low vibration level. Okay. But question is, how do I achieve it? Suppose I have a forging hammer next to it, or I will give you a more realistic picture. I had visited a lab where we are doing some isolation selector for a laser machining, laser measurement system, laser microscope to be precise. In this building there was an elevator. Each time the elevator was going up and down the shaft, they were having problems in their laser based measurements, because once we have an elevator going up and down the shaft, because of the elevator's movement, the vibrations was getting transmitted from the elevator shaft through the foundation to the laser lab. Okay. And the measured vibration levels were even 10 to the power minus 6 g, and that is small enough to create problem in your laser based measurements. Okay. So, as an engineer, as a vibration specialist, we have to decide on what is known as this isolators. Isolators both for motion and both for forces, because you think about earthquakes. When earthquakes occur, why do buildings fall? Because excessive forces have come through the foundation. Okay. So, we have to design and decide on isolators. Vibration is the motion is one. Next, we will talk about cases when we have impulses, nuclear blasts, shock waves. Okay. What happens when we have shock waves? What happens when we have a missile firing on the deck of a ship? Okay. So, how do we arrest that the ship should not rock? Okay. Other electronics and the equipment and the control panel should not get affected, because once we have such shock waves coming in, they are going to give rise to fatigue loading. Shock coming once, shock coming twice, repeated shocks, they will induce fatigue load on the machine, and then the structural components, maybe the electronic solders would fail. Imagine a printed circuit board, okay, wherein we have a lot of solders, and this printed circuit board is kept on a platform wherein very close to it you are firing a missile, and there is no protection to arrest the vibration caused once you fire this missile, and this forces are going to excite the solders, and solders will give away eventually, okay, and then you will have a component failure. So, the reliability of the equipment has to be also ensured that they do not fail under repeated shock loading, repeated forces, repeated motions. So, this has to be also ensured. Yeah, this is another example which I was talking about, and you must have seen this. When we have this generator driven by an engine, and because of this motion of the engine, because the engine itself, because of the inertia forces and the gas forces are going to have, and you must have studied in your dynamics of machines, that some of these forces are not balanced. Okay, whatever we call a perfectly balanced machine, but then there are some orders at which balancing forces are there, and these forces will also excite the foundation, and this has to be isolated by, I could have elastomer mounts, but nowadays people are using cable mounts. This cable mounts, it can flex in both directions, longitudinally, transversely. So, it can take up forces in any direction, because if I was talking about an anti vibration mount, which you will see that the mount which we have is usually in one direction, say. Okay. But suppose the motions are in 3 directions, it becomes very cumbersome to put 3 isolators in 3 directions. Rather, the convenient way of doing it is through cable mount, or sometimes in people also known as wire rope mount, because of the fact that there are no elastomers here. So, they can be subjected to weathered conditions in the saline atmosphere, in an oil mist full atmosphere. So, they will not wear out with time, and because of these are made of high strength stainless steel, they will not corrode, they can take more load for the same available space. So, cable mount is people are particularly in the defense, they are using a lot of cable mounts because it can survive a lot of harsh environment. This is another case of a missile launcher, and then here you see again the cable mounts have been put here. And such a system could be put on the deck of your ship. Then once you have the missiles firing, none of the motions are going to go through the deck to the other systems in the ship. Okay. Of course, you will see we will be doing certain numericals, how do we calculate the stiffness, how do we estimate the damping, how do we estimate the payloads of the mounts. Well, this is from a catalog of a manufacturer of isolators. I will just show you some of the examples here. These are the normal helical springs which are used as mounts, and some of these are actually pads where there are pockets here. For example, when you compress them, they are going to flex in and take in the load. These are the cable mounts, and these are some of the conventional spring helical mounts, and there could be a series of such springs, and then there could be a damping associated with damper associated with it, and so on. I will now give you a typical example as to, say for example, I have a machine. Okay, I will just draw the base of the machine, and suppose it is put on 4 isolators. And then there is this machine has a certain mass m. Each one of them has a stiffness k. So, springs in parallel, the effective stiffness is nothing, k effective is nothing but summation of the k's, and this will be 4 k. Okay. And the natural frequency of this system will be m by 4 k. Okay. Now, imagine the question is what is the motion of this or the vibration which is transmitted to the ground because of this system. This system, say for example, it is rotating at a certain speed omega. There is a rotating component which is rotating at a speed omega, and which is known as the driving frequency. So, we will define a ratio r is equal to omega by omega n. So, the ratio which is transmitted or the displacement is actually given by where zeta is the damping coefficient factor. Okay. And r is the frequency ratio. Now, if I plot this, what happens is, if you look at the typical vibration response plot, now if I increase if the damping reduce is very less, what happens is this amplitudes go up. Okay. And if I increase the damping, okay. So, at resonance I can always reduce the motion, vibration motion, by introducing damping. Okay. Now, how is that done? Actually, there are many ways to introduce damping. In rotational systems, they use what is known as torsional damper, particularly in crankshafts of engine. Another is by damping, coating or sandwiched beams, and they are both constrained and unconstrained. So, basically if I have a surface sheet metal, in the constrained layer damping, what I could do is I will have another thin structural material, and here I will put a viscoelastic damping material. So, because of the relative motion of these two members, there will be an hysteresis loss, and then the energy will be damped, the energy will be reduced, and then the oscillations of vibration will reduce. This is one. Another is just coating with the unconstrained. We just coat it with a damping material, which is known as the kind of a coating. Commercially, a lot of damping paints are available to measure such, or to put on the structures to reduce the motions at resonance. Coming back to this figure here, so this is how the structure of the internal of a vibration isolator looks like. This is a steel base plate, and here there is a neoprene rubber body which gives stiffness and sometimes also gives some inherent damping in it. And so, one component of the structure is attached to the base, another component is attached to the top, and same is true here, wherein we have the neoprene pad or rubber pad. On top of it, we also have an helical spring. So, depending on the payload, we can, if the payloads are more, we can have a bigger helical spring. If the payloads are less, even sometimes the pads are good enough to take the payload. Okay. And as I was telling you in the previous diagram, some of these pads, they have what is known as, they are not a thick rubber sheet, instead there are pockets. So, what happens when there is a load, because of this pockets, if you look at the sectional view, so I am just drawing say two pockets, they will flex in. So, because of a load, they will try to move in, okay, and then try to take the load, and then try to, because we have to arrest motion. So, they will flex and take the motion, and then less will be transmitted. So, such are the neoprene pads which are used as isolators. Okay. Now, such vibration isolators are sometimes used to, in engineering, to isolate shock. Now, what is shock? For example, you would have studied about the vibration, wherein in the time domain I have a series of, if I can break them into in time domain, there will be lot of frequency components of such a time history of the vibration signal. But a shock on the other hand is a large motion occurring for a fraction of a time. Okay. And this amplitude could be very, very high. For example, impact like a gun burst, large impact. They happen only one in a given period of time. They are not repeated. We never have repeated shocks. For example, a large earthquake initial wave is a shock. So, such shocks have very, very large amplitudes. So, immediately what happens, how do we isolate this? Suppose if I subject my equipment to such shocks, they are going to get damaged because of these high oscillations. So, in such a case, what if you look at the energy point of view in shock isolators, if you look at the time, I will, if the energy is like this to begin with, okay. In shock isolation, we try to reduce, and this energy, if there is no isolators, this energy would straight go into your component and damage the component. So, in shock isolation, what we do through this isolator, try to take in all that energy, and it is the same energy, but dissipate it at a lower amplitude with a longer time. So, the energy, the area of these two curves should be the same. So, energy dissipation at a slower rate. Okay. So, if I have a very fast moving object, shocks are coming here. So, this isolators or shock isolators actually try to take this energy, and then the same energy goes into the system, but at a reduced amplitude, because I cannot eat up energy. Energy has to anyway go in, but I will give it at a much slower rate. So, this is how, because how does that happen? This happens by having provisions for this isolators to flex, to move. Unless they move, they cannot take up that energy. Instead, if it was a rigid connection, everything would go in. So, this is a soft connection here, this is a soft connection here. Okay. So, they will have low motions, and sometimes these cable mounts are also used in shock isolation system. We just saw the example of the missile launcher. So, such foundations are also put with cable mounts, which also act as shock isolators. Okay. Of course, this is not a class in vibration, because engineering shock and isolation, or vibration and isolation, is a course by itself, and I am sure the teacher must be covering all this there. But this is a course on condition monitoring, and the reason behind telling this is, once you go to the machines to do CBM, you will invariably come across these elements, and we have to do measurements around these elements, because these are the elements wherein the energies go in and go out. Okay. Because of an unbalance, I will see the forces coming at the bearings. Because of a forging hammer, I will see energy coming into the system at the isolators. Okay. So, this is another example which I will this is on a backhoe loader. Okay. Okay. Typically a backhoe loader or a truck, essentially there are two strong components. One is this engine and the chassis, and if you observe, and this is the unit where the operator or the driver sits, and this is a cabin. Okay. And invariably, this construction equipment, be it a bulldozer, be it a loader, they are always subjected to harsh vibrations because of the terrain, because of the work nature, because they have to shovel, etc. So, these poor operators are really subjected to very harsh levels of both vibration and noise. So, these cabins, they may look very robust, but they are actually supported on 4 mounts, and again our vibration isolator come into play there, and one has to decide on good amount of vibration isolators. This is one example. We are talking about, say, a truck. You all must have seen a truck going on the highway, but the cabin where the driver sits actually sits on the chassis, and this cabin is actually mounted on the cross frames, or the cross frames and the longitudinal rails at 4 mount locations. So, no matter what comes through the road, because of the potholes, because of high speeds, because of undulations on the road, all these motions would normally come into the driver or to the driver's seat. Imagine, I will just give a story here. See, the driver gets excited by a forcing frequency, and if you think of a human body as a mechanical system, the internal organs are supported in a fluid, and then they oscillate. So, these internal organs also have a natural frequency, and this natural frequency is about 2 to 5 hertz, very low frequency. But imagine from the road, if I have a forcing frequency of 2 to 5 hertz coming into the seat on which the driver is sitting, then what is going to happen? The driver is also going to have a resonance at 2 to 5 hertz. The driver will have a nauseating feeling, and maybe he will fall sick, he will throw up. And I am sure all of you must have experienced this while going in those state transport buses, wherein there is not good amount of isolations with the seat and the bus floor. They are almost rigidly bolted, you would have noticed, and then you would be saying people feel uneasy going long distances in such buses. On top of it, if you think of the luxury buses nowadays, when there are good amount of cushions in the seat, good amount of isolations, they reduce this energy coming in from the road and affecting the passenger or the driver. So, I will just show you one example here in this backhoe loader here. This is a particular case wherein, if you can see this actually, this yellow one is the chassis of the cab, okay, and or the backhoe loader, and this is the cabin, and this is the isolator. It is nothing but a thick rubber pad, and here we are actually trying to measure the motion. These are the accelerometers which are used to measure the motion of the chassis. This is in a particular direction, this is the transverse, this is the longitudinal, and this is the vertical direction, and there is another accelerometer here to measure the response at the mount location on the cab side. So, the effectiveness of this isolator or the vibration transmissibility can be checked by seeing the ratio of these, or the difference between these two levels, and this difference is large, then this isolator is doing a good job. So, this is how the isolators are actually evaluated, and then we can also design as to what kind of isolators is to be taken in. And if you look at the force transmissibility curve, suppose I have a body which generates an force F, and there are certain stiffener, damping, etc., and this is the transmitted force F t. Okay. If you calculate this force transmitted to the applied force, this applied force or the force which is originating because of the dynamics of the machine is given by okay. And if I was to plot this curve where r is equal to omega by omega n is equal to k by m, and omega is the forcing frequency. Okay. So, this is 1.0, say this is f t by f, and this has a plot, and this value is √2, okay, no matter whatever is the damping. So, at a frequency of omega by omega n, or omega is equal to omega n by √2 or more. So, that means if the frequency of driving frequency is more than the √2 the natural frequency, the force transmitted will be less than the applied force F. So, the f t by f will be less than 1 for r greater than √2, and this is a very, very fundamental design equation which all vibration designers work with. And so, we can decide on, of course, this, because somebody asks you estimate me the values of k and c to be used in this machine, where this machine operates at say 1200 rpm. So, 1200 rpm means 1200 by 60 is the forcing frequency. I know the mass of the body, I know I have to find out stiffness and c depending on this equation. Okay. And sometimes I can go to the manufacturer's catalog, find out for different payloads what is the available stiffness or available damping, and then select the isolators. Okay. So, to summarize, in vibration applications to engineering, the cases of unbalance, the cases of base excitation, the cases of force transmissibility are very, very important, tuned dynamic absorber and damping, tuned dampers. And vibrations occur around us everywhere, and these techniques which I told you are actually used to reduce the vibration levels, but sometimes we use them, or we use them as an indirect means to estimate the condition of the machine, because if there is an unbalance, this will give rise to forces in the bearings. If the isolators are not working properly, the vibration levels of the engine will go up. If the dampers are not working, the torsional oscillations would be high and the crankshafts would fail. In fact, many of the industries you will see the crankshafts failing because the torsional oscillations were high. They were either not arrested by the dampers, particularly in ships, these dampers are filled with oil. Somebody neglected filling up the oil, dampers went dry, and the effects happened. Okay. So, we have to be careful as to how we can reduce these vibration levels. In the next class, I will be talking actually, I will be giving you more equations, and we will try to solve some problems in rotordynamics, how actually rotordynamics is an offset from vibrations, and how actually rotordynamics help us understand condition based maintenance. Okay. In closing, this is one last slide wherein you will see the tuned dynamic the torsional damper here on this engine. And if you will recall, here in this engine we had done a lot of unconstrained layer damping to the oil sump to reduce the radiative vibration levels, vibration and noise levels. This is actually in an engine manufacturer's test cell where we are doing some vibration studies on the engine, and particularly this is the torsional damper, because there is a crankshaft here and this is a 6-cylinder truck engine. So, this oscillations are reduced by having this torsional damper over here. Okay. Thank you.